I also got confused with the time zones a little bit. I hope that didn't happen to us.
Hello.
Yes, it's always a problem. It's 7 o'clock in Texas.
That's right. Very early morning.
Oh, it's 7 in the morning?
In California. Yeah.
It's 7 in the morning, I see. So it's too early for a seminar. This is Here is about 9 p.m.
Wow.
Yeah.
I'm in Tokyo. So
yeah. International. All around the world.
And Thomas, where are you now?
I'm here at Heidelberg. So for me, it's convenient. It's 2 o'clock, 2 p.m.
Oh, Heidelberg. My wife and my daughter are near Düsseldorf. They're German. Okay. They're Mit-Oma.
I see. Okay. Nice.
And then my other daughter is taking off tomorrow. So the whole family will be near Düsseldorf.
Okay.
Recording in progress.
Mm-hmm.
Should we wait for more people to come in?
Probably we should start on time.
Okay, good. So therefore, let me just share the screen. Hold on for a second.
Do you have this? I think you should have this possibility, but let me check.
Share. No, I think I can do it.
Okay,
do you see the screen now?
Not yet, but we see that. Yes, we see it.
No. Yeah.
Let me see here. And then if I here. Now, do you see one slide or 2 slides?
2 slides. So it's the presenter view.
Okay, like this is better now?
Yeah, now it's great.
Yes, it's fine. Perfect. Okay, so then let me start. So I'm very happy to open our seminar 1 of the 31st Laser Physics Conference and to introduce our first speaker, Frank Canore. Fortunately, he's so famous, doesn't need any introduction. And what he's going to talk us today is quantum state characterization with deep neural networks. And I'd like to thank everybody who joined us, whatever the time you have in your place. And so please, Franca, the floor is yours.
I would like to thank the organizers for their kind invitation. Can you hear me?
Yes.
And let me just put here the pointer here. The pointer is pointer option here. And I would like to Olga for the kind invitation on the organizers. I'll be talking about quantum state characterization with deep neural networks. So therefore, you would like to find out the density matrix based on data. And the data is often noisy and messy. And then, so therefore, if you want to see more details, these both papers are available from our website. It's with a student that was in the group, that was the driving force. He was a student in my group and then postdoc in my group. He left. He was a postdoc in my group for 4 years, then became a faculty and he hired my student in his group. So essentially, these are like a former group member who are still working together. On quantum state tomography using conditional, generative, adversarial networks. So I'll be talking about this in a moment, but adversarial network means you have 2 networks competing with each other. They're adversaries, they're dueling. And then, and how to classify
surgery, digital X-ray, digital dental X-ray, and a full in-house laboratory. Today, this is both diagnosing and treating your pet. Our team of doctors and staff are here to offer
Lazar Papernik,
from wellness exams and vaccination to surgery,
Lazar, would you mind muting?
Therapy, boarding, and
just
more.
A second. I'll
I think the sound is coming from Lazar Papernik.
Animal Hospital. You'll find
I can just disconnect.
Okay, good. Okay, thanks.
Okay, good.
So it's better to keep all the channels mute. So So the idea is to do a classification and reconstruction of optical quantum states with deep neural networks. This is optical in the sense of microwave, but I mean, the same ideas will work in other fields, but we're thinking here about superconducting circuits, but the same techniques can be applied to other ones using deep neural networks. This paper is almost like 35 or 40 pages long. So this one here explains in gore detail the PRL, because the PRL is hard to read because this process is very, very complicated, it's very messy. So it required like almost 40 pages of explanation, but they were published simultaneously, back to back. So we're going to do first the main idea and then explain what generative models are and these generative adversarial networks. And then afterwards a summary and outlook. So let me just start with the summary from the beginning. Quantum state tomography is a challenging task in intermediate state quantum devices. It's very CPU intensive, it's very complicated. So the question is, can you get tomography done quickly? Because initially the computational effort was requiring months and then weeks and then hours, but people would like to do it faster and faster. So this has been a challenge in quantum computation for a while. And here we're applying, it might be the first case perhaps to use conditional generative adversarial networks, CGAN, to this QST, which is quantum state tomography. So these are two abbreviations, but I hope you can remember quantum state tomography, which is our goal, and the tool is this conditional generative adversarial networks. In this framework, two dueling networks are competing with each other. So there is a generator and a discriminator, and they're learning multimodal models from data. So essentially, they're trying to figure out how to fit the data to either a coherent state or a GSC state or a Bell state or whatever, Fox state, whatever, and then or a coherent state. So therefore, we improve this conditional generative adversarial network with custom neural network layers that enable the conversion of the output from any standard neural network into a physical density matrix. This will explain afterwards. To reconstruct the density matrix, the generator and the discriminator networks, they are training each other on data using standard gradient-based methods. So therefore, there are two neural networks competing with each other and trying to improve and this is what happened in the case of when the top master of Go was beaten by computers, because two networks were training each other. If you put a network training with a human, it takes too long. You put two networks competing with each other, the training process is very, very, very fast. And you can, principle, beat chess players, you can beat Go players, etc. So we demonstrate that these quantum state tomography, conditional generative adversarial networks can reconstruct optical quantum state with high fidelity. And this is important part, using orders of magnitude fewer iterative steps and less data. And this is the crux of the problem. The procedure is complicated, is messy, but at the end, you want a method which is fast. So it takes a while to set it up. This work took like many years to get that, but is to compete with accelerated projected gradient-based and iterative maximum likelihood estimation, which are the standard ones. So we also show that these conditional generative adversarial networks can reconstruct a quantum state in a single evaluation of the generator network if it has been pre-trained on similar quantum states. So this is the main idea I'll be talking today. So this is the main contribution, is a new deep learning-based quantum state tomography method. Initially, you have some data which is fed into the neural network, and there is some process here involving, there is some noise you can add, which is like trying to mimic Gaussian noise, photon loss. You need to try different noise models, and then reconstruct the data, and then compare what the discriminator will find based on good quality data, and then improve the iterative process. I'll explain this in more detail. So classification, you have a quantum state. Here's this one here. And then you take some measurements. Let's put a qubit interacting with a cavity. And there is a measured signal. There is a data which is very noisy. It's all over the map. It's a big mess. You need to do something which is classification. And the typical classification in neural networks, if you look at any textbook or anything undergraduate, they always tells you the example of a cat or a dog. Can a computer distinguish a dog and a cat? This is very easy for humans. For a computer, it's difficult. Or this was not easy years ago. Now, for us, it's a system in the ground state or the excited state. And then, of course, the data is messy. Because it's just the data is all over, it's noisy all over the map. So therefore, if you make a measurement, it's going to give you this messy result here, but then this will give you some probability to be in the ground state or probability to be in the excited state, and there is a reconstruction algorithm used to do the complete characterization of the quantum state or the density matrix or your matrix product state. So essentially what you're doing like it's an inverse problem here. And then somebody perhaps needs to put the microphone off there. So therefore, there are these two networks. Essentially, this you need to see as a two-player game. It's like in Go or chess. It's a two-player game. So one player is called generator, the other player is called discriminator. But you need to train them together because at the beginning, you need to assume they do not know what they're doing. So they need to just train to each other. The generator generates samples. At the beginning, it's going to be all over the map. And along with real examples from the domain are provided to the discriminator and classified either as real or fake, because at the beginning, everything is going to be noisy or messy. So the discriminator, it's then updated to get better at discriminating between real and fake samples in the next round. It's an iterative process where at the beginning, things are getting very messy, but then eventually they get better and better. The generator is updated based on how well or not the generated samples fool the discriminator, because essentially the discriminator is the one who's going to decide which samples are the better ones here. So therefore, there is here a tutorial published a few years ago on generative network. This tutorial has a nice paragraph. So let me quote it. We can think of the generator as being like the counterfeiter, trying to make fake money. The discriminator is trying to check it, trying to allow legitimate money and catch counterfeit money. To succeed in the game, the counterfeiter must learn iteratively, step by step, to make money which is better and better, which is indistinguishable from genuine money. And the generator network must learn to create samples which are drawn from the same distribution of the training data to be able to detect better fakes. So essentially, they are improving with each other. And that's one way to think of them, is like they're competing. So there is some input which can be put into an n-dimensional vector. You can add noise, Gaussian noise, all kind of noise. And they generate some results. And then the discriminator is going to compare with some bunch of data. Then it's going to say, is it real? Is it correct or not? Or is it noisy or not? Eventually, at the end of the day, you want to classify, either do Wigner functions, data with visual patterns, or these plots of density matrix. If you look at the real imaginary part, you want to know, is it a Fock state, is it a coherent state, is it a thermal state, is it random, is it a number state, binomial, cat state, GKP, or some other kinds. But you can do it on the Wigner space, or you can do it on these density matrices here, which is like the dot here and this one here. So there are many, and sometimes the whole thing is mixed up together. It's a bit of and then it gets a bit messy because it could be partly thermal coherent or cat and GKP. So the whole thing can be mixed up together. So therefore, the two-player game, there is some input, which is typically noise, generates result, generates a sample. The discriminator is trying to figure out if it is okay or not, and then it's going to update the model back and forth, and then both on the generator part and on the discriminator part, because this has to be better at doing better samples, and this one here has to be better at checking which ones are real or not. So the two models are competing against each other. They're adversarial in the sense of game theory, because they're playing a zero-sum game. So when the discriminator successfully identifies real or fake sample, it is rewarded or no changes needed, and the generator is penalized with a large update to model parameters. So therefore, they're like, so the adversarial in the sense of like in game theory. when the generator is full in the discriminator, it is rewarded, or no changes needed in the model parameter, but the discriminator is penalized, and the model parameter needs to be updated. So initially, they're going to create all kinds of errors, but then over time, they're going to get better and better. So now, deep neural net means the following. Typically, neural networks have one layer in between, but if you put 3, 4, 5, 6 layers, becomes deep. But the computational cost when you go from 3, 4, 5, 6 is huge. This needs to be done over and over and over again. So it's computationally, this can be very, very, very expensive. You need to use this NVIDIA chips, which are just very, GPUs, which are very, very expensive. So therefore, you have an input. And then you input into your neural network, and there are some parameters. And then at the end, this you can think of it is as a function. As a function of the input and as a function of the parameters. So it's a nonlinear function with the parameters. The parameters can be learned. It can be modified. Imagine you want to approximate the function. You want to approximate y of x. So this is your goal. Your goal is approximate y. And you do it over and over and over until f, it gets better. But you need to learn the parameters to get better and better, because initially f is going to be all over the map. It's going to be really bad. So you iterate over and over and over to minimize this, because this is the criterion, and then you choose the parameters to achieve this goal. But the beginning is not going to happen. I mean, f of x is way outside y of x. It takes over and over and over. So this is the main idea. Input, parameters, you need to change the parameters to optimize some goal, to achieve a goal. So therefore, the classification connects to discriminative modeling in machine learning. So you need to compute some probabilities there. And then like in this case, you have some input data and then some parameters which you're going to modify over and over and over until you get better parameters. There's the data, there's a neural network, and there is here some function of the data and the parameters. Yeah. Now, reconstruction connects the generative modeling in machine learning. So therefore, you have here some input here is put in a vector, sometimes called latent vector, and then you generate some samples. And then you can estimate some probability density from here. So you're approximating or sample this probability data. So estimating it. When you do that, then you do it here, and then your discriminator needs to compare the generated data with a training set, and then you need to iterate back, called backpropagation, if it is good approximation or not, back and forth. This called the input is like also called latent space. You add some noise because data is typically very noisy, and then you generate a sample, compare with a whole bunch of libraries here and discriminator, and you keep doing this over and over and over. So this here, in the case of optical quantum state, is a qubit and a cavity generating very noisy signal. And then from here, you can obtain, let's say, I versus Q, so either Bigness distribution, or you can put it on phase space plots. And you want to characterize the optical state because you're trying to do bosonic error correction or different kind of bosonic error correction codes. You need to be able to visualize the patterns in the data. If you see the quasi-probability distributions, you can see this pictorial image of the data as a function of time, because the circuit is not static. The system is changing from, let's say, from a cat state to a to coherent state or some other state. You can actually see it easier by looking at the picture, because often it's going to be a big mess. It's not going to be neither A nor B, but something in between. So you can actually monitor. So it's an example here of a density matrix. Let's say this fog position base here. So you have here from 0 to 15, and you have some state, let's say 1, 4, and 7 here. And then you do some measurements, could be homodyne, heterodyne, parity photodetector, whatever. You have some observables. And then from this, you can get, let's say, generalized Q functions, or this form here. The Husimi Q function will be when n prime is equal to 0. But in principle, in this case, you put n prime equal to 0, but in principle could be any n prime. Or you can do the Wigner function from these functions here by doing this. So, and then you can get either the Wigner distribution here, or the Husimi function, the Q for 0. This is the Husimic function. This one here is more the generalized with level 2 or level 3. So in this case, you put n prime equal to 2, n prime equal to 3, and you get these different generalized Q functions. So they're all observables. The one most people have intuition is the Wigner function, but I know some other people just they prefer the Houdini function. You see. So you can choose whatever function you want. You want to do Q0, Q2, Q3, no problem. And then at the end of the day, you want to know if you get either like this Fock state. I mean, can you do the real imaginary part of the state here, the Fock state, or the coherent state, thermal state, random number, binomial, CAT, GKP, or in this density matrix representation. So this is an example. Once you have noisy data, the neural networks can be trained to learn patterns in data that can be very, very noisy. But then you might need to add either Gaussian noise or more Gaussian noise or spam. There's an abbreviation for, it's a kind of a different kind of a fine noise. You can put a photon loss, you get photon loss that get closer to each other, or mixed states. And then you can simulate noise during training. For instance, this case, like a thermal state. This is more like, this looks like a binomial state, somewhat distorted here. The other ones, it looks more like a coherent state, actually. This also looks like a coherent state. And these are numerically optimized for error correction. You can have also superposition of Fock states. So you can add noise in these models. It could be Gaussian noise or different kind of noises. In the reconstruction part, so what we do is the following. So you do, the data is coming, there are several multi-layers, and the question is it a Fock state, is it a coherent state, is it thermal, CAT, binomial, number state, GKP, etc. And there have been some work in the past done by different groups, like either focusing on qubit readout or Wigner positive versus Wigner negative. This for deep neural discrimination of a multiplex superconducting qubit states. And then again, it's a neural network for detecting multi-mode Wigner negativity. It's a FYS letter 2020. So there are different groups here trying to identify if it is coherent versus thermal. It's a nice paper in identification of light source using machine learning. And this is Crane on communication with spatially modulated light through turbulent air across Vienna. This is distinguished in most superpositions in air. And so there are some other work looking at this classification of states. So we just, I want to make sure that we're not the only people doing it. There have been other people working on this, and ours, I think, it might be more systematic. So therefore, in this case, you have this data plus noise, and then you need to, essentially, there is something called generator loss. You need to minimize some parameters, theta G here. And then there is normalization here. There is some discriminator loss. And at the end, there is a gradient penalty you need to pay on the discriminator side to be able to distinguish between X or Y. But this is more the inner guts of the CGAN architecture. But there are quite a few little steps there. So therefore, there are here some measurement operators, and then you want to learn these probabilities by approximating it or sampling from it. So you have some operator with generative model produces a Born rule. These are the parameters of the generative model. These are the ones you're going to optimize to be able to fit your function there. So the data is there, and then the new network is going to produce some result, and then it's going to be the generator, and this is the data produced by adding noise, and this is what the neural network understands from the data, but then needs to be compared with what the neural network database has, and eventually come out with a good discrimination of what's happening. So therefore, there is a training from scratch. This was done with experimental data on superconducting circuits, replacing the measurement operator to displace parity. And then, so this is the data here, and this is the noisy experimental state close to a binomial state. So therefore, that is on here. And then this distinguishes and indicates that the state is a bit noisy, is messy, but is somewhat close to a binomial state. It's often not very clean. It's often, I mean, the experiments are a bit messy. And then in this case, there was no prior training or assumption on the noise because it just this is just the data comes from the experiment. And then so this is the summary of this part here. So this is, we have a deep neural networks can be very effective for quantum state characterization. This is a new technique that uses generative adversarial networks for quantum state reconstruction. It allows, it's a bit messy, complicated, but at the end of the day, allows a faster reconstruction, the number of iterations, reconstructing the mixed state with much fewer data points, a reconstruction of states for noisy experimental data with arbitrary measurements, and it can handle different kind of noise, and it can also do single-shot reconstructions. So therefore, it's okay. So therefore, this is the summary, and then let me see here. I think at the end, I wanted to put this one here, that it was that the goal was essentially to do quantum state tomography, which is very difficult. And this technique allows you to do it in a faster way. So this is the summary here. And then thank you for your time.
Thank you so much, Franca. And first of all, I would like to know if our chair of our session is already here or not. I can't identify. Suzanne, are you here or not?
I think you can, the new chair, you can take over.
Yes, so that then let's proceed with the questions. So if you have any questions, please unmute yourself and just ask the question, or raise your hand if you wish.
How many more minutes are available?
Maybe 2-3 minutes we have.
Okay.
Well, I don't see any question yet.
If people in the audience would like to see more the gory details, the PRL is not the best way to, I mean, it's a good summary, but the PHYS' research is more like tutorial. It's explaining things step by step, and it tells you what can go wrong, how to fix it, and how. So it's like, it's very, very, very long, and it has a massive amount of detail because the procedure involved is not simple, it's just complicated. But at the end of the day, this was something that people wanted, is to do quantum tomography fast. So the PHYS research will be the way to go. So, oh, Barry.
Okay,
nice to
Barry,
see you.
yes, please.
Hi, Franco.
Yeah.
Can you hear?
Yeah, I can hear you well.
That's good. So just a couple of quick questions. So one was, what is the GKP state? I don't know that one. And then the more serious question was, so this is designed to be faster, but how do you measure how much faster it is for some given level of accuracy? Because presumably there's a bit of sort of guessing sometimes. And there's something wrong with my audio. I have to just check. Okay. Maybe that's better.
Yeah, I can hear you well. Regarding the second question, it's given the same input by using different methods. It was possible to determine that using these two networks training each other provides results with high fidelity and using orders of magnitude fewer iterative steps and less data than both. The comparison is accelerated projected gradient-based methods and iterative maximum likelihood estimation, which are the two gold standards for quantum state tomography by most groups. So therefore, as far as speed, high fidelity is, and in fact, we had the comparison there in detail in the long, but I mean, it is, we're not talking about a factor of 2. This is like a day and night. GKP, P refers to John Preskill. G, I think, is Gottesman. and K might be Kitaev. So a thing is like Gottesman, Kitaev, Preskill, which is a paper from about 20 or so years ago, and is like one kind of state which is used for quantum error correction. I mean, there are all these many different states out there, and this one here is the GKP, which is notation from quantum information.
Thank you.
Thank you so much again, Franca. I'm afraid we have to proceed with the next talk.
Yeah. Okay, well, thank you for the invitation, and thank you for the patience. And then, okay,
so let me just. The second speaker in our session today is Thomas Pfeiffer. Thomas, can you share your screen?
I'm trying to. Let me check. Is this showing?
Yes, it's fine. And so Thomas is from Max Planck Institute of Nuclear Physics from Heidelberg. And today he's talking about multi-photon physics and atoms and machine learning. Thank you, Thomas. The floor is yours.
Yeah, thanks very much, Olga, for the introduction and, in fact, the chance to speak here at LPHYS again. It's a great pleasure. And I would like to give you a bit of an overview of the work that we're doing here in my division. And as I've shown here, this will cover several groups, in particular the group of Anne Hart, who has recently, fortunately for her, unfortunately for us, moved as a professor to Aalen University from a junior group leader position that she had at the Institute. Christian Ott, Jose Crespo, and Robert Mooshammer. And you'll see how a lot of these things, in a way, maybe in the future, may aim in an interesting direction, where I will show a bit of almost a crazy idea in the end that we may want to discuss. So this is this quantum atomic intelligence part. Quantum machine learning, not the usual way as you would think of it. So let me start right in. The structure of atoms, I call it. So when you look at atoms, you can look at them in the energy domain or in the spatial domain. And the interaction with light can be such as you usually do, first principles with just one photon, linear perturbation, theory, first order, exciting atomic states from the ground state, or also ionizing atoms, kicking electrons, one electron out to the continuum. And these processes, these linear processes, are in a way operated to perfection, I would say, in, for example, things like optical clocks nowadays. So where you really try with the highest precision methods in the optical frequency combs to set up an atom such that it serves you as a perfect resonator with an extremely high Q value, so extremely small line width compared to its frequency that it resonates or oscillates at. And you can build atomic clocks with, breathtaking stabilities these days. For example, ytterbium atoms, but also lattice clocks based on strontium atoms here. And this is actually not the end of the line. People are approaching currently, I think, even the 10 to the minus 20 level, also in Junier's group and other places. And of course, also with ion clocks, you can get extreme precisions for these optical clocks. A natural way to extend this would be to go to not just to singly charged ions, for example, thinking of ion clocks, but to something called highly charged ions. Why is this so interesting? So this is Jose Crespo, group leader here in the division. He is one of maybe the global expert on making highly charged ions. So basically atoms from which you strip most of the electrons until just a few electrons are left. And these are extremely inert systems that you can then use, for example, also as the heart of clockworks, of optical clockworks. Why is this so interesting? Because if it's such a small system, it's very inert to external perturbations. So external magnetic fields or also radiation from thermal radiation that would still be existing almost does not perturb these systems. And his group is really worldwide unique in creating ions highly charged ions, for example, embedded in crystals of other ions, beryllium in this case, that you can laser cool. So you have a crystal of beryllium ions that you laser cool to extremely low temperatures. And he manages to implant with his group ions, highly charged ions in these beryllium crystals to sympathetically be cooled down to these extreme low temperatures of these iron crystals. So this was the first achievement in 2015, but he keeps collaborating also with people at the Physikalisch-Technische Bundesanstalt, so the German Metrology Institute, where it was recently shown that you can not only just do precision spectroscopy, but even build optical clocks still in the visible based on quantum logic spectroscopy. You can use these ions here to really drive them, use them as clock transitions, okay? So not within the crystal, in that case, you just use the crystal for cooling, and then you have only one ion next to it with which you do quantum logic spectroscopy. And currently at Heidelberg, we are even continuing on this mission to make these trapped ions even like better, colder, by building superconducting Paul traps in which this is stored. And for example, here I'll show you just an example of this extreme technological feat that is also done in this group here. Having several layers of going down to at first 40 Kelvin heat shielding and then 4 Kelvin, and then finally having this small Hall trap really at 4 Kelvin in a superconducting resonator, which has already by itself a high Q for the radio frequency with which you can then control these ions also, as you can see here, with very high fidelity. You can move around these crystals and distort them for the beryllium, and of course trap your highly charged ions. And the goal where this is going, which is what we started when I came here 10 years almost now ago, it's already time is flying, is to use not just optical light, but high harmonics. So high harmonic frequency combs that you can nowadays build. Several groups have shown this, and we now also have one, I'll show you, to do highly charged ion precision spectroscopy in the extreme ultraviolet, and with the goal really to achieve the next level of precision. You can show in these highly charged ions, you have then transitions really in the XUV, of course, since the electronic transitions get further and further spaced as you go to higher and higher charge states. And you can find extremely long-lived transitions also in these clocks with which you get definitions with Q values that are much, much larger than for these optical clocks. So this is something that you can do in the future. Also, here is a theory paper on what clock transitions by the Keitel group you could use in the future to build your XUV clocks upon. And for this is the setup for this high harmonic enhancement cavity that was built in José's group. So this is this really large piece of equipment, which is UHV compatible, because of course, for these Paul traps, you would need high vacuum environments. And this was already a technological feat also to build this thing, but it works nicely. It produces you harmonics all the way up. Here you can see to the 33rd, 35th harmonic order in argon, different in other rare gases. This is a spectrum of these harmonics, as you can see. And this is also with quite high efficiencies that you can do this and use them for the spectroscopy. You can do more. And this is what I will show in the following. Also moving to higher and higher field strength. This is an enhancement cavity. So this means that you use an oscillator to couple into a cavity and basically to enhance the power of the oscillator within this cavity to achieve really high intensities, because for this optical high harmonic generation, you need on the order of about 10 to the 13 or more watts per square centimeter to really convert your optical laser light to these extreme ultraviolet frequencies. But you can do more with such high intensities in these resonators. For example, what was done is installing, and this is Jan-Hendrik Oehlmann and Janko Nauta's work, I have to say, in the group of José Crespo, installing this velocity map imaging spectrometer with which, and this was Jan-Hendrik Oehlmann's PhD work recently completed, you can, by rotating the polarization state of this IR light in the cavity, so he made a cavity in which it is possible to even tune or rotate the polarization state of the light and keep the intensity the same, such as to do a tomographic reconstruction of the outgoing electrons in this above threshold intense laser ionization of electrons from xenon atoms. And what one can do with this, and this is Janko Nauta's work already done before we had this tomographic imaging modality working, he could use now the fact that we operate here above threshold ionization at record repetition rates, 100 megahertz. He could show he can now go to the lowest intensities ever achieved, and the highest rep rates, obviously, but also the lowest intensities to look at above threshold ionization. Due to the large repetition rate, he just needs a few counts to get these images. So this is a new regime, basically, the low intensity frontier, you could call it, of nonlinear interactions, multiphoton physics in atoms that you can explore with this method. I would like to continue because I want to show you some other things in the end, because this is in fact what our division really is very interested in, not just what is possible with these linear interactions of atoms with light, and use atoms basically, for example, as precision sensors. This is one fine thing to do and very, very important also for search for new physics and things. But what is also interesting is when you start changing the structure of atoms by your intense fields. So on purpose, employ intense fields to modify atoms and their properties, and maybe to discover interesting new things, or that you could also even later use for, who knows, applications with this. And this is our experimental approach. So we employ really a range of light sources in our experiments, from high harmonics in our own labs to intense IR visible laser pulses, all the way also to free electron lasers that we use, of course, at external facilities. Shine this light at atoms, molecules in a very intense fashion, focused on these atoms and molecules, and then perform different detection techniques, for example, reaction microscopes or multidimensional purely optical spectroscopy, to extract a maximum of information about these interactions of intense light with our atoms. So with these purely optical techniques, we can, for example, get information on what happens to electrons still in bound states. As we just drive the atom strongly, the electrons will stay for some time in bound states and modify these bound states. And we can, of course, also look at free electrons and ions, even in coincidence with these reaction microscopes. And I will give you examples for both of these measurement modalities, what recent things we have been done. I start with the work here in Christian Ott's group, who is exploring this photonic sector in the division. And he's doing absorption spectroscopy, shining light through a cloud of atoms, and doing so in intense laser fields, understanding the interaction of the absorption process in intense laser fields. What is happening? And this is sometimes confused, not confused, it's related to attosecond transient absorption spectroscopy, where lots of people nowadays work with also a combination of attosecond pulses and intense fields, and try typically to study how the system changes as a function of time delay to learn about the natural dynamics of a system, for example, after excitation. What we do here is include also this intensity information in our measurements. So we change on purpose the intensity and see what happens. How do these systems change in these intense light fields? And we have come quite some way understanding what is going on. For example, how is absorption modified? Absorption is basically what you measure in the spectrum, the Fourier transform of your dipole response of the system. And now what happens with an intense field present as you excite your system with an attosecond pulse, at the same time intense field? You create, for example, star chips. You modify this internal structure of atoms for a short time. And this short time delta T, it's modified times the energy change, gives you an additional phase on these imprinted on the excited states in the system, for example. And this gives rise to modified absorption line shapes, which look like Fano lines. And in fact, you can find a very nice mapping between this phase shift you imprint to the Fano parameter Q. And we have used this already some time ago to map out really the phase changes even in doubly excited helium. And what you can see, these phase changes are on the order of pi. So 1 pi is changed in the phase of the doubly excited state. And the fun thing to note is here that this happens within just a few femtoseconds of your intense field pulse. So within just a few femtoseconds of this intense driver pulse, we impose phase shifts of pi. And so one way to look at this is, of course, to say this can be used to control your electronic wave functions in these systems, the 2 electron wave functions in this case. But on the other hand, if you think of it, this is also a way to very quickly change, well, the quantum state of your system. And in a way, you could say, in a different terminology, this is a few femtosecond phase gate, even for 2 electron systems. So keep this in mind. We will get back to such things later. We control atoms on very, very short time scales, control their quantum properties. Let me move over to what some recent experiments with the reaction microscope in Robert Mooshammer's group are. So let me first introduce to those of you in the audience who do not know much about this cold trims or reaction microscope idea. So what you do is you have an interaction, for example, of an intense light field with a cloud, a jet of atoms, neutral atoms or molecules, could be anything. And in one interaction of your light with this matter, you create an ion and electron. So the electron is just, the atom is ionized. The electron goes to one side. So you have an electric field applied here. The electron goes to one side. The ion is pulled to the other side onto a different detector. And to confine the electron in the apparatus and not let it fly away, you additionally apply a collinear magnetic field, collinear to the electric field. And this captures the electron on this helical orbit, cyclotron orbit, and you can directly reconstruct from the position and time that the electron hits here what vector, momentum vector the electron had when it was leaving its parent ion. So this is how this reaction microscope works. And what we do in our work in Heidelberg is to apply now these reaction microscopes to interactions of optical laser light, intense optical laser light with free electron lasers or with high harmonics, and look at the time delay and different things, what is happening. So for this, we have one experiment at FLASH, the free electron laser at Hamburg. It's an extreme ultraviolet free electron laser, so not hard X-ray. And this is what it looks like. The nice property about this free electron laser source is that it has variable gap ondulators. So it can be moved in frequency easily, back and forth, can be tuned. And this, and in addition, so this is what Robert Mooshammer built at the FLASH facility already years ago, a reaction microscope that can now be used in conjunction with the FEL XUV light, but also together with an IR laser that is coming here from a laser hutch, and even high harmonics since recently. So we can bring all these things together at Hamburg at this free electron laser facility in a reaction microscope. And the work of Severin Meister here, a graduate student in Robert Mooshammer's group, was looking at photoelectron spectroscopy of singly excited states in helium by ionizing, for example, helium with a combination of an XUV photon from the free electron laser FLASH and IR photons from the optical laser that is installed there. So, and this could be done such that now you can tune your XUV light specifically through individual resonances in the helium atom and the IR to further excite or ionize these atoms. And you can do so, this was also possible, to put the near-infrared laser light into 2 different polarization directions, collinear or perpendicular to the XUV of the FEL. And you could see, all right, there's completely different shapes of your free electron wave functions, so your photoelectron momentum distributions that you measure experimentally, different shapes coming out in this experiment. You can quantify them and compare to theory, which works nicely, but you can also get a sort of simple intuition of what's happening here. Because if you look at really textbook representations of the spherical harmonics, if the laser, optical, and XUV are polarized along the same direction, you basically stick to one magnetic quantum numbers. The quantization axis in this case is always with the NIR. We define it this way. So you only stay in one LM is 0 manifold and always get these shapes. And this looks like it. You will see later, it really is such a shape. If we have perpendicular polarizations, you would use the XUV, for example, to go 1 to the side. So you do one step in M, in LM, magnetic quantum number, minus and plus 1. And then with the IR light, with which you can absorb 1, 2, or several more photons, you can then go up in this direction and access all these states. And you can see this gives rise to these specific propeller-like states that you get here. And since the reaction microscope is not just like VMI, recording only a projection, you can really fully reconstruct with just looking at these individual events, these electronic wave functions in the continuum, and see in this case, for example, this has the 6-fold symmetry, really get these states as you have them from your textbooks. You can do more, and this is what I would like to show here. Olga, we started a bit late. How much time do I have? I think we started 5 minutes late. I will just keep going. I hope you will interrupt me when I'm done. So this is the next thing here. I will show you, again, a reaction microscope experiment, but not using a free electron laser and an intense IR field, but using a train of attosecond pulses, high harmonics, also in conjunction with near infrared, and this time on hydrogen molecules. Why is this interesting? So this was an experiment also carried out in Robert's group. In fact, Anne Hart was the key person in this. So this was really work of her group with Robert. When the idea was to do attosecond phase control of Bell-like states, at least. So is it possible to change on an attosecond time scale the relative phase in these sort of what you could call Bell-like states, plus minus, and in this case we do not mean the spin of the electrons, but we mean the parity of their wave functions. So plus minus, you have two electrons in the hydrogen molecule. One of them is in a gerade, the other one in a ungerade parity state, and you can make this experiment such that you superimpose these two states, plus minus and minus plus, and even have one electron leave the system, and the other one stays behind in the hydrogen molecular ion. So you have basically a situation where you really separate the state as you do in entanglement, as you need to do, and measure one electron and the ion that stays behind to know where the other electron was going. And this was what came out of this. So we measured as an experimental observable the asymmetry of the electron and ion going either the same way in the experiment or opposite ways, electron one way, the ion the other way. And we found out that on a time scale of 1 femtosecond, basically around 1 femtosecond, this asymmetry was changing from electron departing with the ion or opposite. And I won't have the time, I think, to go through the details of this. People have shown earlier already this natural entanglement exists in these systems just by one photon interaction with molecules. For a long time, people have known there is, of course, since correlation exists in the ground states of molecules, when you photoionize these systems, you get, of course, states that you could call entangled, and this entanglement shows in these measurements. The question is, can we control this entanglement that naturally arises in these quantum systems? And there are the first experiments also here in the group of Mark Racking, photoionization also of H2 molecules by choosing a specific pair of XUV pulses. They could show that they can create more or less entanglement. So the degree of entanglement is changing here as a function of the attosecond pulse pair separation in time. And we ask the question now, is it possible to modify this relative phase phi in these Bell-like states? And I cannot give you all the details. As I've shown you, we control this relative phase by doing a sort of rapid type measurement, but now not working with the IR laser, imparting the phase on just one electron, as you would usually have in attosecond time delay measurements, but now we can do this on 2 electrons. And it turns out, by going through this, I will have to skip this, I'm too slow today for some reason, or at least I'm not sure whether I watched the time correctly. You can calculate the relative phases the 2 channels have that interfere here with each other. So you have one channel that is just one XUV photon and departs on the ground state of the molecular ion, and another contribution from a pathway that absorbs a lower harmonic, one IR photon goes to the free electron, changing its parity, evolves out, and then another absorption of an IR photon on the bound electron occurs. So you can now split the interaction of your IR field between a free electron and a bound electron, and these 2 pathways interfere and give rise, in the end, you can just go through WKB theory on a very simple, it's of course an involved calculation, but it's really a simple principle that gives you the key or main physics behind the process. Of course, you could go into much more detail, but this is in principle what's going on, and shows us that really indeed we can control this relative phase and basically flip, if you want, if you would interpret this in the Bell language, from the triplet state plus here to the singlet state by making a minus in a way. Yeah, this is what you could do in principle with such an approach. Okay, and just to summarize this part, so coherence and entanglement come together currently in ultra-fast physics. So people are moving their way from atoms, already early experiments where you looked at wave packets of Rydberg atoms in molecules, looking at vibrations later on in the late 80s, 90s, going to molecular ions, as Mark Racking's group did, but also Robin Santra showed that if you have now an internal degree of freedom in the ion that is left behind, you can play with this entanglement property of these systems, but it was never really measured in coincidence. And this is the experiments that are now coming up here, as I said, group of Anne Hart with Robert Mooshammer, measuring really this both particles, an electron and an ion, to get closer insights on this entanglement of these systems. And for the very last 2 minutes, I hope I have.
You have one.
Okay, I have to make them this very short. So this is what I would call this the crazy idea that I wanted to present. Where are we going? Why are we interested in this coherence and entanglement on short time scales? And this is what people here call the rise of intelligent matter. In fact, they do this in optical systems. So there's groups working on how they can, for example, build, as we've also just heard in the talk before by Franco, like networks, but in the optical, based on optical chips. So directly with light, and recognize, for example, even handwritten letters by choosing optically these different couplings between nodes on a chip. And people have already had the idea to translate this to high harmonics as the optical resource. But what we were thinking, why not use atoms directly, and atoms really with their states as sort of classifiers, registers for classifying, for example, letters or digits. And this is the idea that we had here as a team with Professor Matthias Wollenhaupt, Professor Manfred Lein, 2 colleagues, where we came up with the idea, could we possibly train atoms such that they can recognize handwritten digits, for example, by just choosing the right code that we program the atoms with. So we choose polarization-shaped laser pulses in which we encode the letters or digits in one direction, whereas we encode the code that steers, that tells the atom what to do in the other polarization direction. And we just have to find the right code that would always make one state in the atom maximum when it sees, for example, the digit 6 handwritten. And it turns out, at least running this on a computer, we can find codes that really train the system such that it recognizes 50% of the training set. And that is interesting. It really shows also in a test set that it learns, it generalizes, because guessing would just mean 10% recognition. And using the program you find for the training set with a very simple algorithm, I have to say here, was very, like, just basically one core. One could do way better. You can see that there is the atom doing generalization. It works already on unseen digits that it recognizes those when it was trained. So it seems it's not completely crazy. There are lots of interesting things that you can think about now. This goes beyond traditional quantum protocols, as were already studied with ultra-fast pulses. But here we would use this basically neural network and training idea to tell the atom directly and in a compact system, not really on separate entangled entities, but just directly program the quantum correlated atom and make it do quantum operations. This is, of course, the group, all I've shown of a large group of people. This is just showing our division and our main cooperators that I also pointed out on the slides already as during the talk. And here are a few people in Christian Ott's group, Jose Crespo, that were doing the main work, of course, from what I've shown on the slides, Robert Mooshammer, Klaus-Dieter Schröter, and Anne Hart's group here. And with this, I'm just putting up the summary, showing you this way from linear interactions for clocks to nonlinear interactions, steering and understanding atoms, all the way to looking also at entanglement at short time scales. And in the future, who knows, really using this to also get something maybe applicable out of why we are doing this. With this, I'm done and would like to thank you very much for your attention.
Thank you so much, Thomas. So, Franca, you are the first.
Oh, thank you, Thomas. It's a great talk. In the last part is the algorithm is doing supervised learning, unsupervised learning, or reinforcement learning. Which varieties, how the digits are recognized?
This was a supervised learning scheme, so where we basically told the algorithm whether this was correctly classified, this digit, or not, and then just changed the code. And it was, in this case, as I said, a very generic, simple, really a genetic algorithm that we applied to find this code. Yeah, so we basically use for the phase functions of these program pulses that we have to find here, the program or code pulses, we just use again phase definitions, and we try to optimize the right shape of this pulse to recognize the digit, but it was all supervised. So we always told it, this is correct, this is not correct. And based on mutation cloning and crossover strategies as you do in these genetic algorithms trying to find the code. As I said, this was a very simple first approach. I think you can do this way better once one really thinks about how to do this.
Is this done only digits or also letters?
This was done here for digits only. We have not.
It's very limited, just to 0 to 9. I see.
But the fun thing is, you could reprogram it, so it's really just finding the code for the job. I think it would work for letters. You just then need to find the right program code for it to correctly classify the letters. So this would be a reprogrammable thing even, which is just based on sort of the code that you imprint onto the atom. And this is always the same, of course. So when you should recognize digits, you always send in the same code pulse for this. It's not changing, of course, for every letter. This would be trivial. It's always the same code pulse that tells it, now you recognize digits. And for letters, it would be another code pulse. And who knows, maybe one could find, not in a, so this was a simple 20-level system. In a complex atom, as you actually have, you may even find the one pulse that correctly classifies then digits and letters. There is lots of quantum states in these systems that could be sort of certainly capable of recognizing digits, letters. If you know the right pulse and have found this, it could do this all at once. Yeah.
Oh, okay.
This is the idea. Yeah, thank you. Good question.
Okay, if there are no other questions, maybe I'll ask a short question. So high harmonic generation typically gives you a very broad width of each harmonic defined by the duration of the pulse. But the advantage of intracavity high harmonic generation is that the width can be very small, right?
That's right.
And so how small? Is it a fraction of hertz? What determines this width?
So one has to distinguish two widths. So the width that you see, for example, here is always the width that it gets from basically from the pulse duration that is oscillating in the cavity. The inverse of the pulse duration will be this width. The specific feature of the high resolution of the frequency comb is that each of these harmonics here itself contains about 100,000 million or several millions of comb lines, which you do not resolve here in this spectrum. But each of these teeth that you see for the harmonics itself has a comb underneath that has these millions of modes. And those are on an order of hertz. People have shown hertz stabilities for these harmonic combs. By beating two harmonic combs, Junier has shown this, two harmonic combs, or his group, two harmonic combs that beat with respect to each other. And they have shown, I think, sub-hertz stabilities of these individual comb lines of the harmonics.
I see.
Or these subcombs. Yeah? This is the actual frequency comb, which is basically underneath each of these harmonic peaks.
Thank you. Well, I think we have to proceed because we're quite late already with both talks.
Right.
So thank you once again, Thomas. And
thank
so the next speaker in our session is James Paul from Oxford. Can you share the screen, James?
Yep. Hi, everyone. Maybe you can hear me okay.
We can see you. Yes.
You can see me? You can hear
screen.
me?
Yes.
You can see the screen?
Perfect.
Great.
Yes.
Good. Okay. Yeah. Well, so yeah, not sure what's best to do with the timings, but I'll just blitz through it and let's see how far we get. And hopefully we don't run over too far. So thanks again for inviting me back to talk. So I'm with Professor Alex Lvovsky at the University of Oxford. I gave a talk in this online LPHYS last year on our work with optical neural networks and how we train those networks. And we've got some exciting new results to share on our experiments we've done over the last 12 months on implementing what we call optical backpropagation. So implementing the actual backpropagation algorithm that are used to train neural networks currently in optics. So let's see if I can advance the slide. So yeah, so our work is motivated by the rapid development and widespread use of machine learning across all parts of society and in research. We've seen a couple of examples of directions that people are taking machine learning, and in particular neural networks. So if we kind of stop and think about how we're performing neural networks at the minute with digital electronics and compare it to kind of the original idea of people modeling neural networks based on the brain, there's orders of magnitude difference in the speed and energy efficiency that we're currently performing neural networks versus how we do them in our own head. And the reason why that there's that disparity in speed and energy efficiency is this idea of performing them digitally versus performing them in an analog fashion. So rather than turning all of your numbers and weights and everything into zeros and ones, can we perform that process in a kind of single analog domain? Is there a technology that allows us to do that? And optics is the obvious answer to do this, right? So we can use interference and diffraction of light as the light propagates to perform these arbitrary linear operations and somehow construct a physical analog neural network that can perform these tasks for us. And so that's what our group is looking at. And before we kind of dive into the optics, I just want to do a really quick recap. Apologies if this is kind of way too basic for the audience, but what do we actually mean by a neural network? And so if we take kind of a really simple example task, we want to use this system to classify images, for example. So is it an image of a cat or is it an image of a dog? How do we actually go about doing that? Well, we need to somehow find or construct a function f that's going to map our inputs to our outputs. And we're going to find that particular function. We're not going to specify it. We're going to find it by constructing layers in our neural network of parameterized weights, right? So linear interconnections between neurons that we can update and tune. And in each layer, we're going to have these updatable weights and some activation function, some non-linearity that kind of makes this system more expressive. And we stack up multiple layers with linear and non-linear aspects to it to create this deep network with lots and lots of weights that we can tune. And it's tuning those parameters that's training. And that's our real focus, is how do we perform that training, that tuning of these parameters to do that in optics. And so to do that, we need to choose a platform. So there's a variety of groups that are doing this in all sorts of different ways. As Thomas kind of alluded to, there's this idea of using integrated photonics and weight banks and MZI meshes and all sorts of different platforms. But we do it in free space optics. So we can encode the kind of the linear connections, the neurons in the field amplitudes in different spatial modes. We can connect those neurons and perform the linear connection using spatial light modulators, so liquid crystal displays and so on. And the nonlinear function can be any optical phenomenon that performs a nonlinear effect on the modes individually. And yeah, again, just to highlight, there's lots of groups working on this and lots of different platforms. It's a very exciting field. So let's move on to how we do the training using optics. So as I mentioned, we need to kind of tune these weights and parameters in our network to find the correct function f. And the way we do this is essentially gradient descent. So we pick some loss function at the end of our network that somehow encodes the deviation between what our network is predicting and what the actual ground truth example is. And then we apply lots and lots of examples, and we calculate the gradients of our loss function with respect to all of the weights in the network, use those gradients to update the weights and iterate until that loss function reaches a minimum and converges, and when we've represented the function that we want to. And that whole process is supervised learning that Franco alluded to as well. And so how do we calculate those gradients? Well, it turns out we need two things to calculate the gradients. We need the activations of the neurons at every layer going in the forwards direction, and we need the errors calculated with the famous backpropagation algorithm. So at every stage, every time you send an example through your network, you're going to have a forward passage through the network, measure and tap off all of the activations, and then perform this backward propagation step where you calculate the error from your loss function and you move it backwards through the same network. And that's the backpropagation algorithm, and that's precisely the procedure we want to try and implement optically. So we've kind of looked at this. This is kind of what my talk last year was on. Many people can use the optical system to just perform the inference. So you would train your neural network problem offline on a digital computer. You would find the best weights, and you would then kind of upload those weights to your optics and just use your optics to perform inference, perform predictions on new data. But that has a few kind of disadvantages, and particularly around the kind of the error and the noise and the aberration that your optics might demonstrate. It's a noisy analog system, so it's not ideal to train it on a digital computer. And so what we showed is what we call hybrid training, where we involve the optics in every iteration of that training algorithm by calculating the forward pass optically, so calculating the activations optically, but then doing that propagation step digitally. And we showed that was really good. That kind of was more robust to errors and noise in the optical system, but it still required us to have this digital model, this digital hardware to calculate the backpropagation step. And so the question becomes, how do we do this whole thing optically? Can we do both the forward and the backward pass in optics? And the answer, if it was just a linear network, is absolutely yes. This has been known for a long time. The linear aspects of the backpropagation algorithm are identical to what you do in the forward direction. So what you can do is you can physically inject the light backwards through the same system. And so this idea of backpropagation takes on a really nice physical interpretation of it's the same light propagating backwards, right? And if it was just a linear system, this would kind of be not trivial, but straightforward. The real tricky aspect comes with the nonlinearity. So the whole idea is, how can we perform this backpropagation with optics going through a nonlinear function? And this is the big challenge. So there's kind of three aspects that this nonlinear optical phenomenon, whatever it might be, has to satisfy. So it has to give you a nonlinear response when you do your forward pass with the optics. That's kind of straightforward. There's lots of different optical phenomena that give you a nonlinear response. But then when you do this backward pass with your optics that's coming through the same system but passing backwards, it now has to have a linear response. And not only does it have to have a linear response, it has to have the response that's the derivative of the nonlinear going in the forward direction. So you have some really complex kind of system where the backward response has to have knowledge of the forward response, but it has to be the derivative. And so it's really unobvious how you might achieve this purely optically without using electronics. And the solution our group came up with a few years ago was to use saturable absorption. So we use a rubidium vapor cell, and we kind of adopt this pump probe scheme that's quite common in spectroscopy, for example. So if we have a forward beam that's very strong and is bright enough, it can saturate the absorption within this cell. And so it will kind of experience this nonlinear transmission. And then we can have our backward signal taking the role of a weak probe. So it's much weaker than the forward pump beam. It can't saturate the absorption, and it experiences this linear effect. And so the question is, does this probe experience the derivative of what the forward nonlinear function is? And the answer, skipping ahead a bit in the interest of time, the answer is yes, but not perfectly, but approximately. And if it's rescaled and within a certain region of values, it approximates really, really well to the derivative. So this idea of a pump probe scheme in a saturable absorption cell can play that role of the nonlinearity in an optical neural network. And so moving on to some of the experimental results. This is precisely what we've been demonstrating over the past 12 months. So here we see the results of using a vapor cell and applying this pump probe scheme. So on the left, we see the pump output as a response to the pump input. We get this really nice nonlinear shape. And then on the right-hand side, we apply a constant probe going in the backwards direction, and the probe response follows really nicely this theory curve. And in that central region, it approximates really well the derivative of the response we have on the left with the forward beam. So this is fantastic. It means we can do proper optical backpropagation through an entire network, including the nonlinearity, which is really important. And so we've set about building and demonstrating such a system, a fully optical neural network with multiple layers, including a nonlinearity, and showing training of this network, including the backpropagation. So what are we actually looking at? How does this work? So we have a 2-layer network, which means we have 2 weight matrices, and we need to update the weights in those 2 matrices through some process. These linear layers are, by the way, are essentially matrix vector multiplication. So that's kind of relatively straightforward to implement optically. So we use a scheme we've been building up for the past few years using spatial light modulators, so liquid crystal displays that encode your weights. And so the training scheme is going to start by applying a forward pass through the network. So it's represented by the red here. It'll go through our first matrix vector multiplier. It'll pass through the vapor cell, undergo this nonlinear response to act as the activation, and then immediately pass through the second multiplier, all as a single optical process. So there's no optoelectronic conversion at any point. It's just an entire single optical process as our 2-layer network. And at each point, we tap off and we use cameras to measure the activations at those 2 layers. So we can calculate the activations optically and store those. And then what we do is we calculate the error for our single example at the output. We re-inject the light back into the same system so that it overlaps perfectly and passes backwards through the network, passes back through the vapor cell, undergoes this pump probe response, and picks up the kind of the term that's the derivative of the nonlinear function that we need it to pick up. Again, we tap off with a camera. We can then measure these error vectors, again, performed optically. And using these activations and these errors, we can calculate the weight updates, apply those weight updates to the SLMs, and repeat for many examples for whatever problem it is we're solving. And so at every step of that training process, all of the maths is being done in the optical system. And so just to show some of our results with the training, this is a kind of really simple toy problem. So a few different kind of geometries of having 2 classes of objects, so blue rings and orange triangles. You feed it the XY coordinates of these objects, and the aim is just to learn the boundary between the different classes. So it might be the concentric rings or the objects in the corners or having the different arches. It just needs to learn that boundary between the 2. So it's clearly a non-linear problem. These are you can't linearly separate these. So it's going to rely on having that non-linear response in the hidden layer. And on the right, you see some snapshots of how this boundary is being learned by the optics over time. And to wrap it up and just to demonstrate that this optical training scheme has some real advantage, we train the same network offline on a computer, take those weights and upload them to the optics, and perform kind of the inference test again to compare the 2. And we see a significant degradation in the accuracy of these boundaries when we train offline on the computer versus when we use the optical system itself. So that's kind of, not only can we train with the optics and perform this optical backpropagation, but there's real advantage over performing that training on a digital computer as well. So I'll just wrap up. There's a nice video we have of kind of one example of this training procedure. We see some camera images. We see kind of how the neuron values are evolving. We see down the bottom how the weights are changing, and we can see the boundary slowly converging to these rings. We can see the loss function decreases. We can see the accuracy increases. So it's really quite nice. So in the interest of time, what are we, 20 past? Yeah, I'll wrap up there. Thank you very much for your attention. Thanks to Professor Lwowski and the rest of the group, and to Dr. Shanshin Gao as well, who's kind of the brain behind quite a lot of these these experiments. So thank you very much.
Thank you so much, James. Great talk. And on time, thank you. So, Frank, please, your question.
No, I didn't have a question. This is a clapping, is the clapping symbol.
I see. Okay, good.
I'm practicing my skills with Zoom
if
here.
If somebody has a quick question, please unmute yourself and ask it immediately.
I have one question. So thank you for your talk. Question is, do you have verification schemes to check the correctness of output results?
Right. So we just do these very simple tasks. So you can kind of just tell by the boundary of what's happening whether your system is actually learning these two distinguished classes. So by measuring kind of or visualizing how this boundary is being learned by the optical system, you can see that the task is being completed. At the same time, we calculate digitally on a digital computer at every step what we expect to see, and we can plot what the digital system is performing versus what our optical system is performing, and that's these scatter plots in the middle here. So the theory is the digital calculation, the measured is our optical calculation, and you can see over the process the plots stick to this nice diagonal line or this nice nonlinear line. So there's a bit of noise in the system because it's analog, but it tracks very nicely what we'd expect to see.
Thank you.
Thank you once again, James. Unfortunately, we have to stop this discussion because we are very late. Thank you again, and we are proceeding to the next talk. Chandler, are you ready? Yeah.
Yes. Now let me
share
see.
Your screen.
Yes, I have to share which slide.
And so the next speaker in our session is Chandra Vara from Wigner Center for Physics from Budapest. Please, Chandra.
Yeah, okay. So can you see my?
Yes, we can see.
Okay, so first of all, of course, it's a great pleasure to have this opportunity, and I would like to thank for the organizers for having this chance to share some of my new results. This is a theory talk. There will be a couple of formulae, but not very much. So let me just show you the outline. First, I will give you a very brief background and some partial motivations. Then I will discuss the transition probabilities of intended photon pairs, where I found an exact photon number distribution, which has not been known by now. And then I realized that this distribution in some special case is just a Zernicke polynomial of the parameters. So this is a sort of aberration in the photon number distribution, you may say. So finally, I will give you an outlook. So this is an old thing in parametric processes. You generate, for instance, squeezing. Here is which I show you with the cursor, the quadratic interaction, which causes the squeezing in a degenerate case. And this can be used for noise reduction or amplification. And here I just show you one of the systems in ALI. These large intensity systems, nowadays almost exclusively use parametric amplifiers, so not regenerative amplifiers, for in the CPA techniques of the stretch. Then the stretch part goes to the parametric amplifier, and then it is compressed, etc. So partially my motivation was that to see to what extent is it important whether these fields are truly coherent or deviations from coherence, etc., etc. Because for large intensity processes, this may be crucial. Now, and you know that, let me just quote this very first paper on the generation of photon pairs in parametric processes. So A and B photons are generated, etc. And you can consider entanglement, where here you can use such kind of interaction to generate entangled pairs, which are used in optical imaging, quantum imaging, sorry. So, I mean, this is an old thing. Here, for instance, in this recent book, you can find a bunch of new advances and also some history. So now, please have a look at only those formulae which I point to. So here I just compare the non-degenerate, so non-degenerate and degenerate amplifier algebra, so to say. So in each case, there is a common thing, namely these quantum operators for the photon, they satisfy an S1.1 Lie algebra. But the difference is, of course, the invariance, so the Casimir operator. So, for instance, in the case of parametric interaction, there is a, so to say, constant of motion, which is the difference of the photon numbers, so the two modes. So, and I realized that algebraically, this is very similar to that object which I defined in my earlier paper for phase, regular phase operator description. So look at this. This is essentially equivalent to have, so for instance, the absorption of two photons can be formulated in a way that an absorption of this pair. And so if you formulate it this way, then you again get S1 Lie algebra. And in case of exact resonance, you can just write down immediately the propagator or the evolution operator. And where here the parameters are depending on the source, polarization, frequency, etc., etc., and free propagation. So this is common in all these systems. And now, if you start, and I was able to calculate the matrix element of this evolution, so which means that if you start from a number n of these pairs, and you go over to m, then you get such kind of expression, which is exact. And so where here you have the Jacobi polynomial. And so if this is zero, this is usually, let me just show you. From the vacuum, you get this very well-known Bose distribution, which is this. On the other hand, if you have a larger initial number of pairs, which may come from some earlier source, if you have various steps of these parametric interactions, then you have various photon number distribution. And that's very remarkable that if this new parameter, which is the difference, absolute value of the two, the number of photons in the two nodes is zero, then you have, of course, this, which is just a Zernike polynomial. Here, rho is essentially the tangent hyperbolic of this coupling constant, the modulus of the coupling constant. So it has a well-defined physical meaning. That's very interesting that you have these Zernike polynomials, so which means that all the things which have been worked out in classical optics for aberration, you can take over to quantify such kind of processes by just analogy. So this I have shown you. This is another example for the photon distribution of the pairs, where here I start with 2 photons, and here 3 photon pairs. So maybe I just go through very quickly on the classical aberration. So if you have this Gaussian reference sphere, and in case of ideal imaging, you have a localized spot for this as an image of this star or this object. Now, so depending on the various imperfections in imaging, you have many sorts of aberrations, spherical, coma, stigmatism, etc., which can be nicely quantified with the Zernike polynomials because they form a complete set of orthogonal aberration functions. You can find very nice pictures on various Zernike polynomials, complex Zernike polynomials, cosine and sine type, etc. So, for instance, in case of spherical aberration, you can nicely quantify these radial imperfections. So, and I have to mention that recently the mathematicians, in case of multi-resolution analysis and voice transforms, wavelet transforms, they use discrete Zernike polynomials, which can also can be taken to this quantum situation. So let me just show you just as an illustration. So still, let's consider the Zernike case, so not the most generic. So you have the number of photons in both modes the same. So I mean, they are coupled, of course, as always, but the difference is 0. And if you start at n equals to 0, this is a spontaneous parametric time conversion process. Then and plot the dependence on the excitation parameters. So here, the radial parameter is just that tangent hyperbolic of psi in the evolution operator, which depends on the susceptibility, etc., etc. And the phi, the phase on these plots is the relative phase of the excitation and the generation. Now, so this is the reference. Here there is, as I would say, no aberration. Now, if you start with 1 and calculate the emission probability, then you receive another figure. So this shows a little aberration in this terminology, though I have to very much emphasize that this is not completely a genuine quantum phase space. This I could introduce, I have introduced, but I do not have pictures for that. Here I just have on the axis the parameters of the excitation, so the parameters of the evolution of the electron. I could introduce a number phase Wigner function, which I have done. It is not shown here. And then you would get for the true phase space distribution finite Fourier series of Zernike polynomials. So this is the next step which I have to. This is another example, and here you can of course calculate what is the situation if you have a superimposed state. So this is 0 plus 0 minus 1 pair superposition. Then, of course, the photon number distribution is distorted considerably. And this is for these other cases. So I think I stop here. So I just went through very quickly on some background, and I showed you some formal details which are important in this context concerning the S1.1 group, which is essentially the evolution operator is a unitary irreducible representation of this group. And that's important because for a theoretician, that's a good tool to perform calculations. I have derived the Zernike as the most general transition probability. And in a special case, I have the Zernike polynomials. I made a little detour just to flash a couple of things concerning the classical aberration in classical optical imaging. And and these formulas can be used for various situations almost without change. For instance, the Rydberg atoms, so if you consider a hydrogen system, that can also be converted to S1.1 system if you use square parabolic coordinates. And then you can nicely describe stretching and squeezing in a real space of the distribution. And if one thinks of the minimal coupling interaction, there you have an A-squared term if you expand it. And so you have the photon number squared and the absorption, so A squared and A dagger squared also. Or there is a crosstalk in case of several modes. And then you nicely have these generators, and you can use a very similar mathematical formulas to describe, for instance, the interaction of Dirac particle with two circularly polarized modes, for instance. I will talk about this tomorrow. So where the pump is the relativistic electron itself for the two modes. And there are extensions or reinterpretations of all these results for several modes, which is an interesting generalization or application of these formulas. So I think I stop here, sorry. And I'm thanking you for your attention.
Thank you so much, Chandra. Very interesting results. And so if there are some questions, please unmute yourself and proceed with the questions.
I have one question. So thank you for your talk. If this is a clarification, if I understood correctly, we can see impact of aberrations by using Zernike polynomials.
You can process very nicely with the help of Zernike polynomials because that's an orthogonal system.
So my question is, what about the Wigner function? So whether we can see these aberrations in the Wigner function?
Yes, I have done that. Unfortunately, I did not show you. I should have shown you. I calculated the number phase Wigner function. So which depends on the photo M. So not the usual Wigner function, but the number phase, because the number and the phase is also conjugate variables like P and Q and the L2 representation. And I tangentially mentioned that here you can easily calculate this if once you have these matrix elements containing in the special case the Zernike polynomials, then you have a finite Fourier sums for the joint distribution of number and phase. So, and in that, all these aberrations will manifest themselves. And I am almost sure that for an ordinary Wigner function, you can also see something. There is a massive difference. Here, the parameter space is limited to the unit circle. On the other hand, for the Wigner function, you have the complete plane. So one has to be clever to somehow make some transformations and such. I don't know whether I answered your question or I just wanted to indicate.
Thank you. Thank you. I just wanted to know. Yeah.
Yes. Okay.
Okay, it's the last chance to ask the question. Please unmute yourself and ask if you want. I don't see any raised hands. Okay, if not, let me thank all the speakers of our session again. And in about 20 minutes, we have our plenary session. So please stay here at the same link. Okay, thank you once again to everybody. See you soon again.
Professor Sandu, are you there?
Yes.
So yeah. I think we can.
Sandor is my Christian name.
Okay,
Varo is okay. Yeah, just because in Hungarian we have a reversed order.
Okay.
Okay.
It's clear. Thank you for.
I just.
First question again. So my Wigner function, because Wigner function has all the information of the density matrix, and it means that we can visualize that by using Wigner function. So in your case, you are saying that by using Zernike polynomials, you can see clearly aberrations which cannot be seen clearly in Wigner function.
No. They can be converted to each other. So if you calculate the Wigner function, then anyway, in the most general case, you have certain matrix elements in it. If you start with the wave function, which is expanded in the photon number eigenstates, okay? After all, your Wigner function is an infinite sum containing cross Wigner functions, these Laguerre polynomials or whatever, between the photon number eigenstates. Now, okay, so this is the connection, and here I have these matrix elements for this special evolution operator, which contains all the matrix, so I have all the exact matrix elements. So I can build up a Wigner function, and the advantage of these is that here the building blocks of the Wigner function are the Zernike polynomials, would be, which are themselves orthogonal, you see? So it may be, I suspect that if you convert all this description to the Wigner function, you can perhaps better, for instance, compress data. You see, if once you have an orthogonal system for the transition matrix element, so it's, you see, this is not an accident that people use Zernike polynomials in the control of deformable mirrors. Because if you have a deformable mirror and you have all these aberrations, they can be nicely expanded by Zernike polynomials. And say, these Zernike polynomials have two indices. And if you have, say, 10 Zernike polynomials or 100 indices, then you can just do the control just by storing these numbers, like in the data compression, etc., etc. You see, so I expect that these could be used in this kind of tomography, so to say. This is a speculation. Partly I have done something, but in the number phase Wigner function, not in the PQ Wigner function, because that is easier. So it fits to my regular phase formally, which I did not. Let me just show you. I quote in the abstract of my talk two papers, essentially. These which appeared in 2015. This is the regular phase operator. And the other one is just last year on the squeezing transition matrix elements, which discusses the degenerators. And I was very much surprised that no one has published during the 90 years or such this exact matrix element for the squeezing operator, you see. People calculated moments, etc., but the explicit form, which is expressed, by the way, by Gegenbauer. Let me just show you. So somewhere I have this is. So, for instance, the matrix element of this has not been known, you see. And in this paper, I found this is the Gegenbauer, and also you can nicely calculate the black body radiation, way to squeeze the black body, which is also.
What about non-Gaussian states? So you have shown.
This is squeeze. So I mean, this is general because the initial state is a photon number eigenstate. So you can compile any sort of superposition from this. So these are the most fundamental building blocks.
Mm-hmm.
So it is perfectly general.
Mm-hmm. Okay. And what about information extraction? So regarding this aberration, it is clear. Any other information which we can see by using Zernike polynomials?
You see, in principle, no. I mean, the question is whether it can be because of their orthogonality and maybe if you expand things and you can be satisfied with fewer terms if you have a good basis or something like that. I'm planning to calculate the entropy of things in order to see how the entropy depends on the cutoff of the basis and these kind of things. I would like to do. But at the moment, I cannot perfectly definitely.
Because in Wigner function, we use heavily Hermite functions or
Yes. Yes, that's clear. So the cross Wigner function between the Hermite is just the Lagarde polynomial.
Yeah.
So this is I know all that. So I mean these order, but all these functions live on the complete plane. You see.
Yeah.
But these Zernike things, they are in the unit circle somewhere, and so it's not an accident that they can be used nicely for finite pupils and these kind of things.
Yes. So diffraction, yes, this is good that you are showing the pictures where diffraction is considered. So this.
Yeah. This can be all done with this. Here I just borrowed these figures. If once these people put so much labor to plot these things, I mean they plotted. So why should I plot? I mean just for illustration purposes, because they are just the same functions. But I found in a completely different context. So
my question is, can we represent Laguerre or Hermite polynomials into Zernike polynomials? That I don't know.
Well, certainly, yes, you can. But I think that's you have to perform transformations of the variables.
Yes, some transformation.
Yes. So here in these Zernike, for instance, this rho is essentially the tangent hyperbolic of the modulus of the interaction, roughly speaking. So the modulus of the interaction can be very large, infinitely large in principle, which would correspond to the Hermite or Laguerre case, when you have an infinite extent for the Holder space of the wave function. Because that's an L2 and then from minus infinity to plus infinity for the Hermite. And here you have the tangent hyperbolic. Of course, the tangent hyperbolic goes only from -1 to plus. So somehow, but it's not always trivial to see the correspondence between. But you could expand. I'm almost convinced that there is a.
I will check the book which I am using Grabstein and Rijik.
Yes, yes.
So maybe that book explains.
Yes, and in Born Wolf, you can find a nice mathematical summary on the Zernike polynomials in an appendix. But Grabstein, Rijik, Born Wolf. That is the standard of this book. That's clear. And but of course, in Grabstein, Rijik, you find many things. So.
Thank you. Very interesting.
Okay. Thank you very much for your interest. Okay. Bye.
Bye.
Hi, Oleg.
Recording stopped.
Hey, Olga, how are you?
Fine. Hello, Christoph.